Okay, here's a more complex circuit involving capacitors, inductors, and resistors. And we'll solve for finding the current flowing through the bottom leg to the right using phasors. Let's begin. So first comes the recognition that we can use phasors to solve this. It's because it's sinusoidal steady state. The only driving forces in this are sinusoids, pure cosines. The only driving forces in this are sinusoidal sources, and they've been on forever. There are no switches. So our first step, after recognizing we can use phasors, is to convert it into the phasor domain. Now it's important to understand that when we convert it to the phasor domain, it's not the same circuit. We've redrawn it in a different domain. We can change it back to the original circuit, but we're writing in a different domain. We've changed it from a circuit involving time-varying sources to a circuit involving DC, unchanging, complex sources, and changed our capacitors and inductors and resistors to all complex-valued resistor-like things we're going to call impedances. So we need to change our capacitor. So to find the impedance of our capacitor, or Z sub C, so that's going to be 1 over J, and our omega here is 2 from the source. And that gives us 4 over J, but we're not done yet. 1 over J is equal to negative J. To see that 1 over J, if we multiply it by J over J, that doesn't change it, anything. We're multiplying it by 1. But that leaves us with J over J squared. And we know that since J is equal to the square root of negative 1, J squared has to be equal to negative 1. So this is J over negative 1, which is just negative J. So that is a relationship you'll see a lot, that 1 over J is equal to negative J, and therefore our capacitor's impedance is minus J times 4. The impedance of our inductance, remember, is J omega L, and since our omega is 2 and our L is 1, that's just equal to J2. We don't have to change the resistor at all, but we do always need to keep track of what we're trying to find. And now we can write it as an uppercase letter because it's a DC value, and now we've changed everything into the phasor domain. So now this is really like a simple circuits 1 problem, and there's lots of ways to solve it. I think you see that this is really just a current divider. So although you could solve it using mesh or nodal, let's solve it in one step using the current divider equation. And remember, the current divider equation is that it's equal to the source times the other impedance that you're not trying to find over the sum of both. That's right, that resistor and that inductor just added because they're like two impedances in series. They're like two resistors in series. They are two impedances in series, which has a value of just 1 plus J2. So this looks like a pretty complicated equation, and it is. And you don't need to solve it. You just throw it in your calculator and let your calculator solve it. Your calculator will spit back that it's equal to 8.94 at an angle of negative 16.5 degrees. And so now you can convert back into the time domain. Don't forget your units, and that's the answer. The biggest issue I see students having trouble with is they don't feel comfortable treating these capacitors and these inductors, once we convert them into phasors, just like resistors. They're now all resistors. The second thing I see is that students will get the answer in phasor notation and say, well, that's my answer. And it's not. It's a complex number. It's a phasor representation of your answer, but you've got to bring it back out of the phasor domain and write it in the time domain. So let's review. The first step of the phasor analysis method is to recognize that you've got a phasor analysis problem. You have a phasor analysis problem if all of your driving sources are in this form of a sinusoid with no switches, no U of T's. In that case, you definitely want to use phasor analysis. Your next step is to convert to a phasor domain. The next step is to analyze using DC methods, just like you did in circuits 1. Here we happen to use a current divider. Be able to use current dividers, voltage dividers, resistor simplification, only now it's going to be called impedance simplification, Norton transforms, Thevenin transforms, mesh analysis, and nodal analysis. They all work perfectly well with complex phasors. And the last step is to convert back from the phasor domain back into the time domain. And that's it.